Hello everyone, today we'll talk about spatial analysis methods for sustainable cities. This course focuses on spatial analysis methods that transform urban data into meaningful insights for sustainable cities. While urban datasets such as POA and population provide essential information, they only become truly valuable when analytical methods are applied to understand spatial patterns, relationships, and inequalities. Spatial analysis matters because most urban challenges are inherently location-dependent. Issues such as access to services, congestion, environmental exposure, and social inequality cannot be fully understood without considering where they occur and how they relate to the surrounding urban structure. By the end of this course, you will understand key spatial analysis methods used in urban planning and sustainability studies. You will learn how these methods support evidence-based decision-making and prepare for applying them in real-world case studies, which will be explored in the next course. Spatial analysis refers to a set of analytical techniques that use location-based data to explore patterns, relationships, and processes in geographic space. Rather than simply displaying data on a map, spatial analysis seeks to understand how spatial features interact and influence each other. It is important to distinguish between visualization and analysis. Visualization shows where things are located, while analysis explains why certain patterns exist and how different spatial elements are connected. Spatial analysis adds interpretive and explanatory power to maps. In urban planning, spatial analysis plays a critical role in supporting evidence-based decision-making. By revealing hidden spatial dynamics, such as service gaps or accessibility inequalities, spatial analysis helps planners design more sustainable and equitable cities. Sustainability in cities is commonly understood through three interconnected dimensions: environmental sustainability, social equity, and economic efficiency. Each of these dimensions has a strong spatial component that influences how sustainability outcomes are distributed across urban areas. Location matters because services, resources, and environmental impacts are not evenly distributed within cities. Some neighborhoods may benefit from high accessibility and infrastructure investment, while others experience limited access and higher exposure to risks. These spatial differences directly affect quality of life and resilience. Spatial thinking allows urban planners and decision-makers to identify and address these inequalities. By analyzing where sustainability challenges occur, cities can design place-based solutions that respond to local conditions rather than applying one-size-fits-all approaches. Density analysis examines how people, activities, or services are concentrated within urban space. It is a fundamental method for understanding urban intensity and identifying areas of high demand or pressure. Different types of density can be analyzed in urban contexts. Population density focuses on where people live, while activity or service density reflects where economic and social activities are concentrated. These two density patterns often differ and provide complementary insights. Density matters because it directly influences infrastructure demand, service provision, and environmental impact. High-density areas may benefit from efficient service delivery but also face challenges related to congestion, pollution, and resource pressure. Understanding density patterns is essential for sustainable urban planning. Heat maps are commonly used to visualize spatial concentration patterns in urban data. They help identify hotspots and clusters by showing where people, activities, or services are most densely located. This visual representation makes complex spatial patterns easier to interpret. Kernel density estimation, or KDE, is a widely used method for generating heat maps from point-based data such as POA or event locations. KDE creates a continuous surface by smoothing individual points, allowing analysts to observe broader spatial trends rather than isolated locations. While heat maps are effective communication tools, they also have limitations. The choice of parameters can influence results, and overly smooth surfaces may hide important local variations. For this reason, heat maps should be interpreted carefully and used alongside other spatial analysis methods. Interpreting density patterns requires more than identifying areas with high values on a map. Clusters must be evaluated carefully to determine whether they represent meaningful urban patterns or are simply the result of data distribution or methodological choices. High-density areas may indicate overconcentration of services or activities, which can lead to inefficiencies or congestion. Conversely, low-density areas may reveal service gaps where populations are underserved. Both situations are important for sustainable urban planning. One common pitfall in density interpretation is ignoring population context. A high service density does not necessarily mean good accessibility if population density is also high. Similarly, density should not be confused with accessibility, as proximity and travel time play critical roles in determining actual service access. Accessibility describes the ability of people to reach services, opportunities, and activities within the city. Unlike simple distance measures, accessibility considers how long it takes and how difficult it is to reach a destination, taking into account travel modes and network conditions. It is important to distinguish accessibility from proximity. Proximity measures how close locations are in straight-line distance, while accessibility reflects real travel conditions such as road networks, public transport availability, and travel time. Two locations may be geographically close but poorly accessible due to network constraints. Accessibility is a key sustainability indicator because it directly relates to social equity and quality of life. Unequal access to essential services such as healthcare, education, and employment can reinforce social and spatial inequalities. Measuring accessibility helps planners identify these disparities and design more inclusive urban environments. Service area analysis defines the geographic area that can be reached from a given location within a specified travel time or distance. This approach allows planners to understand how far services can realistically reach under actual network conditions. Isochrone analysis is a time-based form of service area analysis. Isochrones represent areas that can be reached within specific time thresholds, such as 5, 10, or 15 minutes. These thresholds are particularly useful for evaluating access to essential urban services. In urban planning, service area and isochrone analyses are widely used to assess service coverage and identify underserved neighborhoods. By comparing accessibility across different areas, planners can make informed decisions about where new services or infrastructure investments are most needed. Accessibility in cities depends strongly on the chosen travel mode. Walking, cycling, public transport, and private vehicles each provide different levels of access in terms of travel time, cost, and physical effort. As a result, accessibility outcomes can vary significantly depending on how people move through the city. Multimodal accessibility analysis considers multiple travel modes simultaneously. This approach allows planners to understand how accessibility differs for various population groups, including those without access to private vehicles or those with limited mobility. Considering multiple travel modes is essential for inclusive and sustainable urban planning. By analyzing accessibility across different modes, cities can identify inequalities, promote active and low-carbon transportation, and design mobility systems that support a broader range of users. POI-population relationship analysis examines the balance between service supply and population demand within urban areas. In this context, POI represent the locations of services and facilities, while population data reflects where demand originates. By analyzing this relationship, planners can identify areas where high population demand is served by a limited number of facilities, creating pressure zones. Conversely, areas with low population but high service concentration may indicate inefficient allocation of resources. Understanding POI-population relationships supports evidence-based urban planning. It enables decision-makers to allocate services more equitably, reduce spatial inequalities, and improve overall accessibility within the city. Urban movement does not occur in straight lines. People move through cities using street networks, pedestrian paths, and public transport routes. For this reason, network-based analysis is essential for understanding how cities actually function. Network distance differs from simple Euclidean distance. While Euclidean distance measures straight-line proximity, network distance accounts for real travel paths, intersections, and constraints. This distinction is critical when analyzing accessibility and mobility. Network-based urban analysis is widely used to evaluate service reach, connectivity, and mobility patterns. By reflecting real travel conditions, it provides more realistic and actionable insights for urban planning and sustainability. Centrality measures are used to evaluate the importance of nodes and links within a network. In urban contexts, these measures help identify streets, intersections, or locations that play a critical role in movement and connectivity. Two commonly used centrality measures are betweenness and closeness centrality. Betweenness centrality highlights elements that act as bridges or connectors within the network, while closeness centrality identifies locations that can be reached efficiently from other parts of the network. In urban analysis, high centrality streets and locations often correspond to areas with high accessibility, economic activity, and urban vitality. Understanding centrality patterns supports decisions related to mobility planning, service location, and sustainable urban development. Navigation-based analysis evaluates POI accessibility using real travel paths rather than straight-line distance. By measuring access along transportation networks, planners can understand how easily people can reach services under realistic urban conditions. This approach accounts for turns, intersections, one-way streets, and other network constraints that influence travel time. As a result, navigation-based analysis provides a more accurate representation of urban movement compared to simple proximity measures. Navigation and POI relationship analysis supports planning decisions by evaluating service performance in real conditions. It helps identify areas where services appear close on a map but are difficult to reach in practice, supporting more effective and sustainable urban planning. Terrain plays an important role in how people move through cities and how infrastructure performs. Elevation changes and slope can significantly affect walkability, cycling comfort, and accessibility, especially for elderly populations or people with limited mobility. Key terrain layers used in urban analysis include digital elevation models and derived slope and aspect layers. These datasets help identify areas where physical conditions create constraints or increase effort required for movement. Terrain-based analysis is commonly used in walkability studies, accessibility assessments, and infrastructure planning. By incorporating physical constraints into spatial analysis, planners can produce more realistic and inclusive urban solutions. Spatial inequality refers to unequal access to services, opportunities, and infrastructure across different parts of a city. These inequalities often emerge when services are concentrated in specific areas, leaving other neighborhoods underserved. By combining accessibility analysis with population and socio-demographic data, planners can identify vulnerable locations where high demand coincides with limited service access. These service gaps represent critical areas for intervention. Understanding spatial inequality supports evidence-based and equitable urban planning. It enables policymakers to design targeted interventions that address disparities and improve access for disadvantaged communities. Urban decision-making rarely depends on a single indicator. Cities are complex systems where accessibility, density, environmental impact, and social factors interact. As a result, multi-criteria spatial analysis is often required. Multi-criteria decision analysis combines multiple spatial indicators into a single evaluation framework. Indicators are weighted based on their relative importance, allowing planners to compare locations or scenarios systematically. Scenario-based analysis enables decision-makers to explore alternative planning options and understand trade-offs. This approach supports transparent and defensible decisions in sustainable urban planning. The ultimate goal of spatial analysis is to support decision-making. Analytical results must be translated into actionable insights that planners and policymakers can understand and use. Visualization plays a critical role in this process. Maps, dashboards, and indicators help communicate complex spatial analysis outcomes in a clear and accessible way. Effective communication increases trust and usability of analytical results. Spatial analysis supports both strategic planning and operational prioritization. By linking analysis to decision contexts, cities can move from data exploration to informed and sustainable action. While spatial analysis is a powerful tool, it also has limitations and risks. Analytical results depend heavily on the quality and completeness of input data. Poor data quality can lead to misleading conclusions. Scale and resolution are also critical factors. Analysis outcomes may change depending on the spatial unit used, and inappropriate aggregation can introduce bias. Understanding these limitations is essential for responsible analysis. Ethical considerations, including data privacy and responsible use of analytics, must be taken into account. Sustainable urban planning requires not only technical accuracy but also ethical awareness. This course demonstrated how spatial analysis methods can be used to understand urban patterns and support sustainable city planning. Accessibility, equity, and realistic representation of urban movement emerged as central themes. Selecting the appropriate analytical method is critical. Different urban questions require different approaches, and analysis must always consider local context and data limitations. By applying spatial analysis responsibly, cities can support evidence-based planning and make decisions that contribute to long-term sustainability and resilience. This course focused on spatial analysis methods that transform urban data into meaningful insights. These methods provide the analytical foundation needed to address complex urban challenges. The next course applies these methods in a real-world case study focused on integrated POI and mobility analysis in an earthquake impact context. This transition allows learners to see how analytical techniques are used in practice. Together, courses 431, 432, and 433 form a complete learning pathway, moving from data foundations to analysis methods and finally to applied decision support in urban contexts.